Flat glass is a key resource in the materials palette for designers and engineers of the built environment. Two key factors must be considered when assessing sustainability in glass design and use: material efficiency and energy efficiency. Material efficiency is associated with the extraction, processing, transportation, construction, and end-of-life strategies for glass products. Material production accounts for 23% of greenhouse gas emissions globally. Glass, in the form of container, flat, glass fibres and pharmaceutical products, accounts for 4% of this total. The production of glass is an energy-intensive process. Carbon dioxide emissions arise through the combustion of fuels for energy to heat the primary raw materials, and due to thermal decomposition of carbonate raw materials. Additional indirect carbon dioxide emissions are incurred due to the use of electricity from non-renewable sources. Deploying circular economy principles in the design and production phase of architectural glass directly influences opportunities for redeployment at the end of life. For example, the glass type will influence the reuse and/or recycling options. Connections with neighbouring elements will influence the ease of disassembly, and the service life will influence the frequency of replacement and therefore the recurring energy inputs throughout the building life cycle. Energy efficiency is concerned with the operational performance of the building. 30% of global greenhouse gas emissions are attributed to the energy required to heat, cool, and light buildings to optimise the internal environment. The design and detailing of the glass envelope play a significant role in determining the total building energy demand. Greenhouse gas emissions are a key indicator of environmental sustainability. Global greenhouse gas emissions must be reduced by 69% by 2040 to stay in line with net zero targets by 2050. In this video series, we will review how the glass production, use, and end-of-life stages align with this ambitious target. The key strategies to increasing material efficiency in architectural glass can be framed by the 9R framework. The 9Rs represent alternative design and recovery scenarios that can influence resource use. They include seeking smarter methods for product use and manufacture, extending the lifespan of glass products, or investigating useful secondary applications of glass. In this video series, we will explore the functional performance requirements and material efficiency of glass through the lens of the 9R framework. Enhanced material efficiency can be sought at the design stage through smarter product use and manufacture. This forms the first three Rs: refuse, rethink, and reduce. The glass product can be made redundant by abandoning its function or by offering the same function with a radically different product. Alternative transparent materials may provide the same desired function at reduced environmental cost. Alternatively, we can seek more intensive product use. At a building level, this will involve increasing the operational hours of buildings that use glass products through shared ownership and use. For example, commercial buildings that are inactive during the night could provide functional spaces for leisure activities in the evening. Other designs could reduce the use of glass by providing the same function with less material. This is enabled by engineering lighter weight designs or increasing efficiency in glass product manufacture to consume fewer natural resources and materials. For more information, see the Reduce video. The use of glass in the building envelope has a significant influence on the energy and emissions associated with building use. The selection of the glass type, construction method, and overall glazing build-up continue to evolve to meet changing performance requirements. Historically, the influx of daylight was achieved through traditional window systems. Glazed areas would typically account for no more than 30% of the load-bearing masonry building envelope. The 1950s saw the decline of the load-bearing wall, and envelopes were able to take on their own role as cladding elements supported by the principal load-bearing frame of the building. The first curtain walling systems were lightweight single glaze systems that had significantly inferior thermal and insulation performance compared to their opaque masonry predecessors. Buildings of this type relied on air conditioning and space heating to compensate for overheating and excessive heat loss. The emergence of low emissivity glass coatings and the insulated glazing unit enabled enhanced energy efficiency. The hermetically sealed insulating glazing unit consists of 2 panes of glass separated by an argon-filled cavity and metallic spacer bar. Fixings between glazing and framework moved away from mastic joints to neoprene and EPDM gasket designs that formed a better watertight seal. In recent years, structural sealant glazing is deployed as alternatives to polymer gaskets to provide a more durable and aesthetically clean adhesive fixing between glazing and framework. The advent of double-skin facades delivered further improvements in thermal and acoustic performance. Double-skin facades incorporate an additional layer of monolithic glazing outside the insulated glazing unit. Natural ventilation is promoted through the external cavity to minimise air conditioning requirements. The incorporation of blind systems or external louvers can further enhance energy efficiency. Some of these systems operate under automated control strategies that may track the sun. The incorporation of designs that enhance operational performance must be assessed alongside the influence on embodied energy and carbon. This is often referred to as a carbon payback period. The trade-offs between operational and embodied carbon can vary considerably depending on the lifetime of glazing elements. The functionalities of glass have evolved such that glazing is no longer one single construction element, but an integral multi-material component that makes use of a wide-ranging palette of materials and advanced processing and connection methods. These include laminated glass, gas-filled multiple pane windows with low E coatings, thicker insulation, solar thermal collectors, and even building-integrated photovoltaics. These techniques have enabled improvements in safety, internal comfort, and reduced operational energy use. However, paradoxically, the uptake of these complex assemblies can make it difficult to recover glass after its first cycle of use. Complex or multi-component systems complicate the end-of-life disassembly processes and can limit the potential to extend the lifespan of glass after its first use. For example, many adhesive connections are non-reversible, meaning that from a design for disassembly perspective, connected components are difficult to recover at end of life. This, in turn, reduces the available stock of second life glass for redeployment in new designs. After its first use, glass can be recovered for reuse or recycling in the same or alternative forms. Recycling glass back to glass involves high reprocessing temperatures, therefore limiting the environmental benefits of pursuing this recovery strategy. This takes us to the inner loops of the 9R framework, extending the lifespan of the glass product and its parts through reuse, repair, refurbishment, remanufacture, or repurposing. Glazing fabricators in Europe have invested in facilities for dismantling insulated glazing units to allow for refurbishment into new, better performing glazing. Research is also underway to investigate new business models for leasing glazed facade systems, assigning the responsibility of dismantling and repair across the value chain. For more information, see the reuse video. The use of waste glass, also known as cullet, in new glass production can lead to up to 41% reduction in CO2 emissions. On this image, we can see the total tonnage flows of glass in the UK, from primary raw material on the left-hand side through to application, collection, and end of life. The lime green flows indicate glass that is recovered for recycling back to new glass products. Flat glass accounts for around 20 to 30% of global glass production. It is used in the automotive and building sectors. Unlike in the container glass sector, we can see that flat glass is rarely collected for reuse or recycling after its first use. It is typically downcycled into a less environmentally valuable aggregate product, or worse, wasted in landfill. Flat glass manufacturers and glass fabricators do recover glass offcuts for recycling pre-consumer glass, as shown by the light green flows on the image. In the UK, post-consumer glass is rarely recycled back to flat glass, although new private initiatives are investing in the necessary logistics to promote this in practice. In some countries, such as the Netherlands, organisations have invested in take-back schemes for flat glass. Within these schemes, glass manufacturers pay a small fee for every metre squared of flat glass produced. This funding is used to provide the necessary storage, transportation and reprocessing for post-consumer flat glass to be recycled back to high-quality glass products, such as float glass, insulation products and container glass. For more information, see the Reduce and Recycle videos. As shown in this video, sustainability in architectural glass is a complex subject that must be assessed with a whole life cycle perspective. All life cycle stages require equal levels of industry and political attention. New research and industry developments to unlock the economic, environmental and technical opportunities associated with material and energy efficient glass design are essential for enabling a sustainable glass future. Thank you for watching this Open Glassroom video in which we introduce the idea of sustainability in glass. If you'd like to learn more about the concept of sustainability, have a look at the videos of this series where some of the R strategies are described in depth. Our references and further materials at the Open Glassroom platform.